The Predator's Purpose: Intention Perception in Simulated Agent Environments by Amani Mainashilos, Cynthia Hom, Kevin Ginta, and George Montanes of Amistad Lab for CEC 2021. This paper is one of 3 total projects covering survival advantages of intention perception in simulated agents. Our first paper, Predator's Purpose, specifically discusses the mechanics of target awareness. Our second paper, The Hero's Dilemma, focuses on intentional stance by other agents. The last paper, Gopher's Gambit, differs from the first two and takes a unique approach by studying intention based on artifacts that have been left behind as opposed to other agents. Our main goal for this experiment is to evaluate the benefits of intention perception, which is the ability of an agent to perceive the intentions and plans of others, in improving a software agent's survival likelihood in a simulated virtual environment. In order to model intention perception, we set up a multi-agent predator and prey model, where the prey agents search for food and the predator agents seek to eat said prey. We then analyze the difference in average survival rates between prey with intention perception, knowledge of which predators are targeting them, and those without. To portray a predator-prey simulation, we wanted to incorporate a targeting system in which a predator selects a prey to target and chase. In accordance to this, we designed our predators to target the prey that they intend to eat, shown visually here by the connecting red lines. A predator's only objective is to catch prey and has no need to worry about getting eaten themselves. Predators know the locations of all prey within their range of awareness and stochastically select one to target, with a closer prey having a higher likelihood of being selected. At each moment during a chase, predators have a small chance of re-evaluating which prey to target, when perhaps there is a new closer prey which would make more sense to chase. Our prey survival involves eating food and steering clear of predators. Prey know the locations of all food within their range of awareness, and are more likely to move towards food if it is close or if they are hungry. Both predators and prey have measures of stamina to slow them down if they move too fast for too long, and are given incentive to stay close to the center of the environment. Prey also have 4 different tiers of awareness. The lowest tier is no predator awareness, which means the prey can only see food. The next tier is proximity awareness. The prey are aware of the location of nearby predators and can try to avoid them accordingly. The highest tier, which is intention awareness, grants prey the ability to know when a specific predator is targeting them, and subsequently focus on running away from those specific predators over others. We also have a cautious tier of awareness that will be explained shortly. We then test whether a prey's ability to detect a predator's intention gives a measurable survival advantage over simple predator proximity awareness, and over even simpler predator obliviousness. Because intention-aware prey focus on running away from predators and take fewer risks than other prey, one might worry that any benefits observed are due to mere caution rather than knowledge of intention awareness. To address this concern, we implemented a cautious prey, which acts on paranoia rather than intention perception. We retrieve data on how often intention-aware prey are targeted by predators and for how long, and use this information to occasionally make the cautious prey think that they are being targeted by a random predator, regardless of whether that is true. In practice, this means that cautious prey are proximity-aware prey that will sometimes put emphasis on running away from particular predators, just like the intention-aware prey, except that these predators may or may not actually be a threat. This decouples the knowledge from the behavior and strengthens the link between intention awareness and increased survival rate.
Here we describe the properties of our agents. The sight distance is the radius of an agent's vision, while the sight angle is the range of angles covered by the agent's vision. Prey have a default sight distance of 10 prey lengths and a default sight angle of 360 degrees, while predators have a default sight distance of 20 prey lengths and a default sight angle of 90 degrees. We chose these values because prey like mice and gazelle often have a larger range of vision but a shorter sight distance, while predators like eagles and lions can often see farther but focus mainly on what is in front of them. The max speed is the fastest speed that agents can move at when they are not tired. Agents become tired when their stamina, which starts at an initial value, drops below their tired stamina. They are then considered tired and cannot move faster than 1/3 of their max speed until they restore their stamina back to their initial stamina. On every time step, the agent's stamina decreases if they move faster than half their max speed and increases otherwise. Prey have a default max speed of 31.25 prey lengths per 100 time steps and an initial stamina of 1.5, while predators have a default max speed of 25 prey lengths per 100 time steps and an initial stamina of 1. Both predators and prey have a tired stamina of 0.2. We gave prey a faster default max speed and a higher initial stamina because prey are often smaller, faster, and can run around longer, while predators are often slower and get tired more quickly. Both agents also have a hunger satiety measure, which we simply refer to as hunger. Hunger starts at 1 and decreases by the amount specified by hunger decrement at each time step. When agents eat food, hunger increases by 0.5. The default hunger decrement value for prey is 0.0005, and for predators is 0.0003. We include the hunger satiety property in our simulation so that prey prioritize eating food when close to starvation. The maximum fasting interval is the number of time steps that a prey can go without eating. For this reason, we only have a default value for prey and not predators. The default maximum fasting interval for prey is 2,000 time steps, which we found gave a realistic balance between eating food and avoiding predators. Note that although we have default values listed on this slide, we also vary the values of prey and predator sight distance, predator sight angle, and maximum fasting interval in our simulations. We'll go into the details of our simulation in a later slide. There are two components to agent movement, direction and speed. We'll first talk about how agents decide their direction. If the agent is a predator and prey are in sight, they will choose a prey to target and simply move toward the prey. Otherwise, if the agent is either a prey agent or the agent is a predator that cannot see any prey, the agent will divide the possible directions to move in into 12 bins. We then give each bin a favorability score that is higher if the bin is closer to more favorable stimuli like food, and lower if the bin is closer to unfavorable stimuli like predators. We then pick a bin using a weighted random sample, where the weights are higher for more favorable bins. And then we'll sample a particular direction from the chosen bin using a uniform distribution. Details on how predators choose their targets, as well as the calculation of the favorability metric, can be found in our paper. Let's now talk about how our agents determine their speed. If the agent is a predator that is targeting a prey, the predator will move at 2/3 of its maximum speed. We use the 2/3 factor because predators that are targeting prey continuously move toward a single prey, and therefore have less indecision regarding their direction of movement. So, we reduce the predator's targeting speed as a counterbalance. Prey that are being targeted will move at their maximum possible speed in order to escape the predator. Now, if the agent is neither a prey being targeted nor a predator targeting a prey, we will calculate a speed according to the favorability of the chosen direction, the speed at the previous time step, and some randomness to mimic reality. The speed depends on the favorability of the chosen direction because agents will move faster if they are more certain that the direction that they're moving in is favorable to their survival. The speed also depends on the speed at the previous time step, since animals in real life have inertia, so the speed at one time step is influenced by their previous speed. It is worth noting that in this slide, max speed refers to the max speed of the agent after adjusting for stamina. As mentioned earlier, agents are tired if their stamina has dropped below the tired stamina at a previous time step, but not yet recovered to their initial stamina. So, if the agent is tired, their max speed will be reduced by a factor of 3. This is how the simulation itself works. We spawn our agents in a large, flat, obstacle-free environment. Agents are encouraged to stay within a small circular region since we include a stimulus factor in the direction algorithm that increases the favorability metric for directions that point toward the center of the environment. This is to encourage agent interaction and avoid having simulations where agents stay far apart for long periods of time. Every 70 time steps, we spawn one food. However, we limit the amount of food at any given time step to the initial number of prey in the simulation. By default, we see the world with 5 predators and 20 prey. The ratio between the number of prey and the number of predators is called the prey-predator ratio. The speed of predators is always a proportion of the speed of prey. We call this proportion the speed fraction. In our simulation, we vary the prey-predator ratio, speed fraction, prey and predator sight distance, predator sight angle, and the maximum fasting interval to determine their effects on prey survival. For each set of these varied parameters, we run 1,000 simulations, except for cautious prey, for which we run 100. Each of these simulations themselves is run for 10,000 time steps.
Here we see that a greater proportion of intention-aware prey, those with proximity and attention awareness, are alive at each time step than for prey of any other awareness tier. However, a greater proportion of intention-aware prey die from starvation as well. For the other tiers, the majority of prey are eaten before they have the chance to starve, but for the intention-aware prey, they die much more from starvation than from being eaten by predators. We note that the cautious prey performs better than the proximity-only prey, but still significantly worse than the intention-aware prey. As we vary the parameters, in general we see that the intention-aware prey have the longest lifespans. For the prey sight distance graph, we see a really interesting trend where there is a peak in lifespan instead of a strict increase. It seems that too much information can be detrimental. Perhaps beyond that point, the additional information muddles their priorities and makes them less likely to choose the optimal direction. At low predator sight distances, predators have difficulty locating prey, and thus most prey survive reasonably well. Note that because of the lack of lock-ons, we were unable to properly replicate the cautious prey for when the value was 1, and so that point is excluded. Once sight distance increases, the lifespans drop significantly for those without intention perception, and then increases slowly for all tiers. One possible explanation for the rise is that predators become more likely to switch to a different prey to target when they are able to see more prey. For predator sight angle, we see no significant variation across values. We believe this is because when predators cannot see prey, they turn randomly every time step until it finally locks onto one. Thus, low values do not have a large effect on the predator's ability to find and target prey. In the speed fraction graph, we see a somewhat surprising peak. One might think that lifespans would strictly decrease as predators became faster, but that is only the case for the unaware prey. We believe this is due to hunger. Slightly faster predators can chase prey with awareness towards food that idle prey would not have normally found. The peak is then where that benefit becomes outweighed by the likelihood of being eaten. The peak is likely later for intention-aware prey because they can better avoid fast predators. We also note that at low speed fraction values, proximity and unaware prey live longer than intention-aware prey. We believe this may be because the intention-aware prey will avoid nearby predators that are not a threat since they're so slow, and as a consequence not eat food that they should actually be able to safely get. For the prey-to-predator ratio, it seems that another balance between starvation and being eaten may be behind the peak. When there are more prey, a smaller percentage of them will be eaten, but it will also be harder to find food. Many of the prey that succeed in avoiding predators may also find themselves on the outskirts of the terrain, where they will starve because they are not eating food. With the maximum fasting interval graph, all prey benefit from being able to go without eating for longer, until it no longer becomes a concern and the lifespans flatten out because the sole cause of death is being eaten by predators. This most greatly helps the intention-aware prey, as starvation was their main cause of death to begin with, and eliminating that concern allows them to avoid predators without that consequence. Note that each line in these graphs is surrounded by a nearly imperceptible 95% confidence interval, and thus all visible differences are significant. From those results, we conclude that prey with intention perception have statistically significant survival advantages over those with only proximity awareness or no awareness, showing that intention perception does confer a survival advantage. We saw that prey with intention perception tend to starve more, but are better at avoiding predators, and so survive longer overall in most scenarios. Furthermore, we saw that there is a statistically significant difference between the survival rates of intention-aware prey and cautious prey, indicating that the survival advantages of prey with intention perception are not due to caution. Extensions to this work could include using evolutionary algorithms to evolve predator and prey strategies, rather than using hand-designed motion algorithms as we did here.